Hello everyone. In this second lecture of this half part of the course, I'm going to tell you about the dynamic behavior of slopes and embankments. As it could have been expected, I'm going to start by introducing a case study that shows you how this is important, and I will then follow reminding you of the basic concepts of evaluation of slope stability. And that is something that you may have been already familiar, and as before I can tell you that if it's not a good reminder, then you are more than free to ask me for the materials of the previous course where all these things will be described in detail. But as you saw last week, the idea or the rationale why we do that is because we build up on that to analyze dynamic conditions. All follows up from the static ones. And as before, the dynamic considerations are not in Giro Code 7, which deals only with the static conditions. We will be reminded today, and then at the end I will discuss a little bit about the mitigations measures to prevent the failure of slopes under dynamic conditions. So the case study, of course, relates to a seismically active region, New Zealand, as you are definitely aware, and in particular the Awetier Valley. This case study has been chosen because it's very representative of a typical dam design. It's a 15-meter high by 170 diameters of length in the long crest embankment. As you could expect on many dams of this size, you have an inner core made of mudstone, which is a very impermeable material, and with a para-in section as the height increases, as I'm trying to show now with the pointer here. That's the core I'm referring to, with para-in section made of mudstone. And then you have shoulders along the side of made of alluvial gravel, so very permeable material in relation to the impermeable core. The purpose of that dam is water storage, used mainly for irrigation, and it has a capacity, as you can see, of 250,000 cubic meters. As a result of that, has been classified in the New Zealand Code of Construction as a medium potential impact category. But despite that name of medium, what that means in their context is that there is potential for loss of life, moderated socioeconomic, financial, and environmental damage. So clearly, it's the type of dam that you don't want to see failing. So this dam experienced some damage during the earthquakes of 2013, which are called as the Cook Strait events, which had a magnitude of 6.5 and 6.6. Now, noticeably there is that the second earthquake is not really an aftershock, at least within the standard definition, because it has a magnitude higher than the first event, and is not an insignificant increase. Remember that the earthquake magnitude is on a logarithmic scale, so a decimal point is actually a large increase. So what happened to the dam? It had first, during the first event, the appearance of 100 millimeter cracks in the upstream side of the crest, and they extended during the second event up to 5 times that. Not only that, but the shoulder, the gravelly shoulder, experienced some separation from the core made of mudstone, and it also showed evidence of some settlement. So clearly, a movement that would be considered to be literally scary, and something that could precede failure under any much smaller aftershock. But immediate action was taken, and the level of the reservoir was reduced by 5 meters to reduce the risk of flooding of the downstream in case it failed. And you will be pleased that that was done, because shortly after, under geological terms, and when reparation was underway, there was an earthquake much larger, the Kaikoura earthquake with magnitude 7.8, which of course is much larger, and that experienced additional cracking, but repair works had already started, and that reduced the significance of the damage quite a lot. And of course, there was no flooding downstream because of the precautions that were taken after the first two events. So hopefully that highlights why what we are going to do in this lecture is pretty important. And of course, these concepts are not just applicable to dams, they also apply for embankments, as you can see in these two cases found online, where the embankment of the highway in both cases has been displaced laterally due to the earthquake seismic loads imposed over a certain event. So how we predict those movements, or at least we estimate those movements under earthquake action, is one of the topics that I will be speaking about. You are surely familiar with standard methods of failure in slopes, and you will relate quite well with these planar surfaces or circular surfaces as you see here. But we will be also looking at other types of failure which are well detailed in the Japanese codes, which, as you know, is also a very seismically active area. And those embankments that I showed you in the previous slide are evidence of that type of failure in Alaska, a failure because the foundation ground fails. While the case study that I showed you in Haldun Dam is a case of subsidence of the embankment due to the earthquake loads. And when this happens, normally is the result of liquefaction in the foundation ground underneath the dam. And of course, when this happens, is normally associated with earthquake loads. So we have now to consider different failure mechanisms as well, not just the standard ones that we consider during the static conditions. What I hope you remember at this stage is that when we were looking at the slope stability under static conditions, we use the limit equilibrium method, and that was the same whether we were considering a planar failure of infinite dimensions, as I'm reminding you here, or a circular surface of failure, as I'll remind you later. And the key of the limit equilibrium method is that all we need to do is that we have to assume a failure surface and then identify or calculate the equilibrium of forces along that slip surface in perpendicular directions to that slip surface. So you can see that that is what we are doing in this situation. We are looking at forces acting on that sliding block that repeats infinitely in the upstream or downstream direction. In there we have the self-weight, a reaction normal force, a shear strength of the soil in the sliding surface that we assumed at a certain depth set, and between blocks we have these interslice forces E1 and E2, which are equal and opposite. Once we have identified the forces, what we then do is that we solve the equilibrium in the direction perpendicular and parallel to the slip surface which we assume, which is this straight line parallel to the ground surface at a depth set. And as you can see there, the shear strength of the soil here will be acting against the component of the weight in that parallel direction, and hence S is equal to W sine of beta. And similarly, the component of the weight perpendicular to the slip surface will be acting in opposite direction than the normal force. And that's the key thing to the solution. If we consider the short term, this shear strength will be essentially the product of the undrained shear strength and the length of the slip surface that you can see here. And then we can replace by geometry again the weight of the soil wedge, which is equal to gamma z L cosine of beta. And the third step of the limit equilibrium method is that we compare resisting forces against disturbing forces. And the resisting forces here are CUL, and the sliding forces are, of course, the opposite component, W sine of beta, replaced here at the bottom as gamma z L cosine of beta sine of beta, but the two L terms cancel, and that's why you see them not there. Of course, you can extend this to include groundwater levers and seepage forces, and you can find the factor of safety in the same way by doing a static equilibrium along the slip surface. But if you want to see the full details of how that is obtained, as I mentioned before, just let me know and I can show you the full solution by just uploading the slides into Moodle. Just to emphasize that the problem, whatever the geometry of the slope, we are following the same approach. We have here the case of a vertical cut that I also showed for those of you who were last year. And in this case, during the first step that we assume the failure surfaces, we have this inclined surface. And we are also looking at short-term undrained conditions. So that resistance is in terms of Cu. And then, as you can see by the arrows, we solve perpendicular and parallel to that slip surface. And on the basis of that and some mathematical development, we could also calculate the critical height for a vertical soil with that undrained shear strength and that unit weight. That, of course, could be also extended to long-term conditions, and similarly, after some mathematical development, we can then find the critical height in terms of the long-term or drained parameters C and phi. And even when we have more complicated geometries, all we do is that we assume the failure surface and we calculate the forces perpendicular and parallel to that slip surface, that line. And of course, in a case like this one, when you calculate the weight of that soil wedge to get the perpendicular and parallel forces or components of that weight, the geometry is a little bit more complicated, and hence the formula for your factor of safety is also a little bit more evolved. But the principle is the same, and that is important to highlight here. Whether you do it under the short term, as in the previous slide, or in the long term, as in this one, the principle is the same. You identify the failure surface, you calculate the perpendicular and parallel components of the forces acting on that slip surface, and you consider that they are in equilibrium, so you can then compare resisting against the sliding surfaces against disturbing forces, and that gives you the factor of safety. The principle when you have circular movements, as we did last year, is exactly the same, but the assumption of your slip surface is now not a straight line, but a circle. And that means that what we can compare instead of forces along the line, we're looking at moments along a center of rotation. But again, we have a disturbing moment and a resisting moment, and that is what these factors of safety are giving us. If we do that under long-term conditions, the principle is exactly the same, but what you quickly realize is that you have more unknowns than knowns, and that you need to start making assumptions to solve the problem. And is at that point that the methods of slices appear that I'm sure you remember. And this is the first of the methods that you see during the fourth year, the Swedish method or Felinius's method. And as you can see, is expressed here in terms of long-term conditions. But the principle is the same. You assumed a slip surface that is circular, but you divided the soil mass in slices in the vertical direction, not necessarily equal size in the horizontal. As you can see, they can have different sizes, and what you work on is on the basis of sums of those slices to calculate the factors of safety when you look at forces acting at the base of each of the slices. There are similar methods that do exactly the same, but that take different assumptions, particularly with what happens with these interslice forces E and X, as well as the point of application of the resultant force at the base of each slice, and that's how they differ. Again, full details of that last year, but is here just a reminder. You don't need to do that during this year. What I also said last year is that those circular movements and the assumptions actually apply to non-rotational movements too. You can divide any shape of failure surface or any failure mechanism still in vertical slices, and the Swedish methods equation will be the same when you do the mathematical development, and that's what makes them so popular. Where we stopped last year is that we didn't discuss in much detail what international standards like Geotechnical 7 tell you in terms of slope stability. In Geotechnical 7 there is no provision of a specific equation or inequality to be satisfied in the case of a slope stability analysis in the same way that you get for retaining walls as we did last week, in which the design effect of the actions has to be smaller than the design effect of the resistances. However, there is a paragraph that indicates that a slope stability analysis should verify the overall moment and the vertical equilibrium of the sliding mass. And if horizontal equilibrium is not checked, the interslice forces when using the method of slices should be assumed to be horizontal. What does that mean in layman's terms, following from the introduction that I have just finished by telling you how those methods works? Well, the method is actually telling you what assumptions you have to take to use the method of slices, or in other words, is telling you which methods of slices you can use and which ones you may not use. And that is summarized by people like Kran or by Orr in many publications. And what that translates is to things like Spencer's method is acceptable because the assumptions that it uses include moment and force equilibrium. Bishop's simplified method that I also showed you last year, not unlike the Spencer's method that I didn't mention, that has different assumptions. The Bishop's method, I showed it to you last year, and that is a method that you can use and is compliant with Giro code. Because the assumption in that method is that the interslice forces are horizontal, but things like Jambu's method or Felenius' method that is so popular cannot be used because moment equilibrium is not satisfied. And that brings some challenges. Because again, Felenius' method, the Swedish method, was the method that you could use for any shape of failure surface. And remember how we started the lecture today? We have to consider failure mechanisms that are not standard. So how do we solve that issue? And in particular, how do we deal with those failure mechanisms for slopes under dynamic conditions. That is what Girocode 8 will tell us in the next slide. But of course, what you need to remember is that, as you could expect, in Girocode 7 you have partial factors of safety, and in the case of slopes you have different considerations, because you may have to consider the undrained resistance, and what that means is that you have to use the partial factor of safety of the undrained shear strength depending on which combination and design approach you are using, just as we did with the retaining walls last week or last year in more detail. You will not be surprised if we say that the way that we move from a static slope stability assessment to dynamic conditions is by using a pseudostatic analysis approach, in the same way that from Coulomb we moved to Mononoe-Okabe in retaining walls. And the principle here is very simple and very similar to that case of Mononoe-Okabe, because what we are having now is that we have additional pseudostatic forces Fb and Fh, which are proportional to the static accelerations related to the severity of the earthquake, just in the same way that we had two additional static forces in Mononoe and Okabe, and which they then become a factor of the horizontal and vertical acceleration coefficients. But it's still a limit equilibrium approach in which we still compare resisting forces against disturbing forces, and as a result of that we end up with factor of safety equations under dynamic conditions which are quite similar to the ones as I was showing you at the start of the lecture with infinite planes approaches. It's just that now you have those FB forces and FH forces factored in as part of that pseudostatic approach of analysis. Of course, you would expect that factor of safety to be bigger than 1, because if it's less than 1, the soil mass within the failure surface will slide. And what we normally assume is that it will slide less like a sliding block on an inclining plane. And you are absolute experts already on dealing with sliding blocks, so I don't need to go into the detail of much. Keep in mind, however, that the seismic failure only lasts for a short period of time, unlike the static forces that we consider in the limit equilibrium. Also, as you might be aware, the limit equilibrium provides no information at all about the deformation of the slope or embankment after the earthquake conditions, in the same way that any of the methods of slices under static conditions do not provide information about the deformations. They just tell you whether the slope or the embankment will fail, as on the basis of that factor of safety as we discussed before. But Newark proposed an analogy using the sliding block mechanism that can be used to predict or at least estimate the permanent displacement of a slope or embankment under seismic ground motions. Now, the key principle of Newmark's approach is that the loss of equilibrium occurs only when the applied earthquake acceleration exceeds a threshold value, and the threshold value is referred to as a yield or a critical acceleration. You can put it that in terms of layman's terms, that the yield acceleration is the minimum pseudostatic acceleration that is required to cause stability of the block. So you can assume that not all accelerations will cause permanent displacements of an slope. So you have to achieve a minimum acceleration to actually make that slope to experience a movement. And that means that you have a maximum and a minimum value of acceleration in the opposite directions that actually will produce movement. And that is the case, for example, in this schematic example, that the components or the only parts of that earthquake that will produce movement on the slopes are those that are above that yield acceleration. And the approach that actually what it does is that we take those accelerations and we convert them into velocities and then into displacements that will accumulate by simple integrations that can be performed numerically. So hopefully you understand the principle, but that leaves always more difficult questions. And the first one, of course, is what is the value of the yield acceleration? And then what is the amount of cumulative displacement during a seismic event? The selection of KH which will provide your yield acceleration is crucial and is actually very difficult. If you consider a rigid material for a slope, the inertial force will be equal to the product of the horizontal acceleration and the mass of the slope. And that will of course reach a maximum when the horizontal acceleration reaches the maximum. But real embankment dams and real slopes are not fully rigid, and also, as you saw in the definition, that peak acceleration only reaches a maximum value for a very short time frame. So what we do under practical applications to solve those two questions is that the pseudostatic coefficients KH and KB that we use in pseudostatic dynamic analysis are simply a fraction of the anticipated maximum acceleration, and hence a proportion of the critical acceleration too. Proposed values in the literature are mainly empirical, based on experience and on the very limited, well-documented case studies that we have. What you have to be aware is whether those proportions are a proportion of the free field acceleration, i.e. something that is measured far from the dam, or the equivalent of the PGA that you are already familiar with as well, or whether those proposals are based on the basis of the peak seismic acceleration at the dam crest, because most of those dams, of course, are well instrumented because of their importance and the consequence of their severity of their damage. Two examples of that available experience are the case of Terzaghi and the proposals by SIT in the 1980s. You can see that Terzaghi, long time ago, proposed 0.1 for severe earthquakes, 0.2 for very violent and destructive earthquakes, and 0.5 for catastrophic earthquakes. Those are somewhat subjective descriptions, but people later on added, again, empirical based on experience threshold that relate these descriptions to earthquake magnitudes. And is essentially what SID did in the 1980s, that KH might be in the range of 0.1 to 0.2, but simply as a function of earthquake magnitude. So you don't have to divide like that. And of course, based on that, you always want to guarantee that the factor of safety against dynamic motions is bigger than 1 and hopefully close to 1.15, quite similar to what we expect on the static conditions, and that's part of the rationale of his proposal. British standards, which are still being used at the moment, simply assume that the KH value is a fraction of the peak ground acceleration, as you can see in the schematic. And Eurocode 8, which again is what most of you will have to deal with, has a specific assumption which extends that assumption from Charles of the PGA acceleration, but has a soil factor and a topography factor for the cases in which you have large dams, large embankments, or large inclinations. Please note that the Giro code is based on free field PGA values, just as the sketch is showing you here, not at the crest of the dam. And this chart has here the soil factors for specific earthquake magnitudes and the different soil types according to the shear wave velocities. And I believe that you have already discussed this in some detail with Juan, but if not, how you simply can define the soil types, of course, is on the basis of shear wave velocities or SPT tests or values of undrained shear strain resistance or strength. And again, that's what gives you your soil factor. Remember, as I said before in the previous slide, that the soil topography factor is only when your dam is high enough or your sloping ground is large enough. The rationale behind the soil topography factor only applying for large dams with a height bigger than 30 meters and or a sloping ground with more than 15 degrees is quite similar to what we were discussing last week to account for the inertial effects of the actual embankment dam. And that's why you see that the soil topography factor actually is related to the likelihood of the slip surface depth as well, because the higher you are, the inertial effect gets the bigger. So you can see that soil topography factor, as you can see in the schematic, actually depends on the height and the geometry of the assumed slip surface. An alternative approach that I want to mention, so you are aware of at least some case in which you can use the crest accelerations, is the approach of Markusson, which has KH being equal to a fraction of that maximum crest acceleration. But of course the question is the same. How do we evaluate that maximum crest acceleration or critical value to put into our calculations? So far I have mentioned only how you consider the failure of the embankment or the dam, but we haven't discussed really in detail how to estimate the displacements. Yes, I did mention numerous approach using on the sliding block, but that's where I stopped. Nowadays, McTeasy and Sid proposed some time ago an approach that is relatively frequently used, and that involves 3 steps, which are relatively simple. Keep in mind that their approach is based again on the maximum acceleration at the crest of the embankment and is an empirical approach. How is the procedure? First, they calculate the yield acceleration using slope stability software, and most of those available slip stability software for this case of analysis use the method of slices, and then assume a strength reduction in the order of 10 to 20% of the peak on drain shear strength, because we expect the resistance of the soil to reduce as it strains, as you are well aware. As a second step, they estimate the maximum acceleration at the crest, and then they estimate the seismic displacement as a function of the yield acceleration and the maximum acceleration, as well as the earthquake magnitude. So after they have found the yield acceleration AQI using a software, what they do is that they look at the height set of the crest as a ratio of the embankment of the dam, and then they go down into the graph, and that gives them the value of the maximum acceleration of the crest. that they can expect for that specific dam. Then on the third step, what they have is, of course, ranges that correspond to certain earthquake magnitudes, and then by using the ratio between the yield acceleration and the maximum acceleration that they just estimated, they can make an estimate of the displacement using these charts. This is a major contribution to geotechnical earthquake engineering, and these design curves frequently get updated considering local conditions and as monitoring of case studies continues to appear. And you can see that people like Jonathan Bray suggest some modifications that may be applicable. Simpler methods like the Newmark one, how does it consist using the sliding block? Well, that you calculate the maximum velocity and the maximum acceleration as well as the critical acceleration that actually will produce movement, and then you can estimate the displacement. Richan and Elm's approach is similar but with different empirical coefficients and exponents, and this velocity can be calculated as a ratio of the maximum acceleration and the period of the excitation that is produced by the earthquake. And this can be illustrated by a simple example in which, for example, the maximum acceleration is 0.5 g. That will have an acceleration, a maximum velocity of 0.234 meters per second, assuming a period of 0.3 seconds. If we assume the yield or the critical acceleration to be 2/3 of the maximum, that means that that is 0.33 g, and when we replace everything in there, we get that the displacement will range between 14 and 5 millimeters, depending on the expression that we use. So it's a relatively simple approach, also following the ideals of a pseudostatic analysis, but I hope that you now can put everything together. And as a summary, I did remind you the principles of slope stability under static conditions when we discussed for some time what Eurocode 7 tells you to do and which methods you can use or cannot use. And then we moved on into the pseudostatic approach following from those basic static concepts. And we finished up by showing you how sliding block analysis may be used to evaluate or estimate slope displacements during earthquakes. So I will see you later on during the week for the live sessions. Please be ready with any questions that you may have about this lecture or the previous one, because as you can see, things are so conceptually simple that all you needed was that example at the end. And that is where I will leave things for the live session, apart from any questions that you may have.